I made up a nice intro. I've seen this comic before, but I animated it for us. And then I got I got a little GIF of it too. This is fun. Hope you like it. So it's SN2 versus SN1. So S, substitution, 2, nucleophilic, oh no, N, nucleophilic. 2 means that one has a bimolecular rate determining step. So the rate determining step is the nucleophile and electrophile reacting at the same time. And then SN1 is substitution, nucleophilic, and the 1 means it has a unimolecular rate determining step. So its rate determining step is the leaving group leaving the electrophile on its own to make a carbocation, and then the nucleophile coming in a second step. Sometimes students get confused about that because the ones they think of like it's a one-step reaction. No, it's actually 2 or more steps, but it has a unimolecular rate determining step. So let's look it up. We got the cats here. The gray cat's in the kitty bed and the orange cat's not. The orange cats are nucleophile. The gray cat in the bed is our electrophile. And so the gray cat's the leaving group. The leaving group's leaving on its own. And then this is the unimolecular rate determining step to make a carbocation. Then the nucleophile comes in, leaving group left, and you get 2 enantiomers in this case, the product. What do you think? Which one is this? Is this SN1 or SN2? SN1 it is. And then boom, SN1. And then here we have a nucleophile again, the electrophile with the gray cat leaving group. And the nucleophile is going to come in and kick the gray cat leaving group out at the same time as it comes in. This is a bimolecular rate determining step. So this one would be, you'd get your product. You just get one product in this case, not a racemic mixture. So that's the SN2 reaction, right? I did have a question. It didn't pop up in my chat initially. Could we go over homework later? Lots of them not the same as the answer key. Yeah. So yeah, I don't have answer keys for a lot of the homework from now on, actually, but I have been answering a lot of them in the out in the Jamboards for office hours and the extra office hours. So check those out, but also just ask me. You can if you have a question, you can email me or something too. I won't get to all the answer keys from now on. Do you think you could go over 7A for homework 6? Not right now, but after maybe during the break, if you remind me, Katie. All right, and then so we're gonna do announcements, chapter 7, but actually I got another one, SN2 versus SN1. Watch this one. So is this an SN1 catalyzed reaction or is it an SN2? It looks like this cat's the nucleophile, and it came in and pushed out the electrophile, huh? So yeah, this one's SN2, right? It's fun. All right, so it's best to watch lectures before lab, like I said before. Homework 6 is up, and you should have already done it because exams today and tomorrow. And lab work, you can come in. Oh, lab work you can come in early, but actually this is exam days today and tomorrow. So you could do lab work if no one's in here taking an exam early, but there'll probably be people taking the exam early. I don't want to do lab work during that. And exam details, I gave you a bunch of details in the last couple of outlines. I'm just now reminding you about the early time. You can come at on Monday, Wednesday, today. Not Monday, Wednesday. Today you come at 1 early if you want to start it. Remember, this one's a little bit longer than the other ones. I'll be here too if you want to come ask questions before the exam. And then Thursday, you come in at 10:45 for the 9, or you can come in at 9:45 if you're 10:45 lab student, and 1 p.m. if you're a 2 p.m. student. But come in quietly. Someone's taking the exam. Don't come in all talkative and loud. and set your phone up front and start taking the exam. And then once there's a couple people just finishing up, I'll move them into my office or somewhere good, quiet and safe. And then we can do lab work. Bring colored pens and pencils, or I got some you can borrow. All right, E2 reaction mechanism and energy versus reaction point diagram. Santos has a nice GSA for us. Another honor student GSA. Here we go. Oh, here, let me actually go about this a different way. So if I go to our organic chem step by step, and then I click on animations, you'll see a lot of animations for the chapters we're dealing with lately, right? Well, not a lot, but we're getting more. 6 and 7, we got a lot in 8, huh? Then if you come down, this is sheet 1, this is what I've mostly made. And then sheet 2 is just honor student stuff. So sheet 2, if we go to chapter 7, you see some different things that are very helpful. The SN1 reaction mechanism and energy versus reaction coordinate diagram, the E1, the E2. And so Santos, we haven't looked at that one yet. I'll click through it just really fast. But these are nice to, click through, get the feel of it, and then try a piece of paper and pencil, writing them out yourself and checking by then clicking back through. So here, I'm going to do this one quickly. This one's got 2 products. So we got our leaving group there, 1 carbon away, we deprotonate, get our product. And then the other one, 1 carbon away, we got another 1 carbon away with the hydrogen to protonate, get this product, and then the reaction coordinate diagram, blah, blah, blah. We got different products. And we'll talk more in chat later about why like this alkene has a lower activation energy and it's a little higher in energy than this one. That'll be later, but I won't expect you to know that. I would tell you all this if I asked you to do this reaction coordinate diagram, but I do want you to be able to do them. Like know that they're, their product or reactant flavored, which bonds should be longer, which should be shorter, and the pi bonds forming, people forget that one, and then the partial charges. So these are good practices for you. Just clicking through it fast, you can go back through it later. And that's my lecture outline. Oh, where will you go? My former 12A and 12A and B students, I was wondering where they went. Remember, I've been dealing with trying to advise people the best to transfer, what they should take before they transfer. And it's weird, this is the first year students are being encouraged not to take 12B. So I was wondering where they went before. So I asked the research department, they got back to me. It's pretty cool. So my students who took me for 12A, 12B, and finished 12B spring of 19, 20, and 21, the last 3 years, out of 123 of them, 45 went to UC Davis. I think most all of them had tagged to UC Davis. 23 not reported, so these ones I'm not sure. But then 15 went to Sac State, so that's actually more than I was thinking. That's about 5 a semester, 5 a year. I thought I had less than that. And then 9 to Berkeley, 5 to UC Santa Cruz, UCI, UC San Diego, UCLA, all really good schools, huh? Up to Chico State, Long Beach State, UCSF, got a couple there. I'm wondering if that's like, they must have already had their degree because UC San Francisco is just graduate school. So I'm wondering how that worked. They probably were just taking O.Chem to get into the grad school. And then we got a bunch of them, Idaho State, Cal Poly, UC Santa Barbara. We got Vanderbilt going south, Southern Louisiana University. That's my student, Max. I just talked to him. He's going into a medical lab something grad school next. And Vanderbilt, that was, who was that? It's the Navy SEAL, retired Navy SEAL, really good student. Oh man, I'm forgetting his name. But he actually got a letter of recommendation from me to Vanderbilt and also from a US senator. It's like, oh, cool. Pacific, San Francisco. All right, so yeah, going on to good things. So those of you who are not planning on taking 12B next semester, but still gonna be at Sierra, double think about it, because I don't know, sometimes I don't know, I've had students who don't take 12B for me the next semester and then try to take it the next year, and they can make it. I just once, he just really struggled because it was like he just forgot so much in the year since he took 12. So anyways, there we go. And then any questions about the outline? Najar, I misspelled your name. Sorry. Let me fix that really quick. Najar. Where that A went. It's not misspelled here. Nope. Okay, we look good there. Cool. It'd be fun to have cats and dogs. We got to get some like service cats and dogs. They'll serve as stress relief. Okay. Let's get back into chapter 7. So we went over some SN1 and some rate law stuff. Carbocations. The Wigglies. All right, let's get on the Jamboard and start doing some examples. So what I'm going over today, I'll be doing these SN1, SN2, E1, E2 stuff, and I'll be going into more detail than the simple ones on the exam today and tomorrow, but listening to it will be very helpful still. And I mean, well, it'll help you with the final exam, because that's, it's going to be on that, but then also it'll even help you with today's exam. It's just more practice, more knowledge. Okay, here we go. I want you to help me make up some, let's make up some very fast reactions, some fast, high yielding reactions. So let's do a very fast SN2. Oop, SN2. So what kind of electrophile do we want for SN2 if we want it to be the fastest SN2? Help me out. Do we want that electrophile to be methyl, primary, secondary, or tertiary? We want methyl because methyl electrophiles have the least steric hindrance for the backside attack. And for the methyl electrophile, we want a really good leaving group. What would be a good leaving group? Iodine's really good because when you take off iodide, it's an extremely weak base. So when a leaving group comes off, the weaker it is as a base, the better the leaving group. Chloride's a good choice, bromide's a good choice, but iodide's better because iodide's even a weaker base than chloride or bromide because it's acid. Hydroiodic acid is lower than them on the periodic table. It's a stronger acid. It's a bigger atom, so the negative charge it gets spread out over a greater area like a beach ball. More stable, weaker base, better leaving group. All right, so I got a really good electrophile here for SN2. And then can you give me an excellent nucleophile? What kind would be a really good nucleophile? Do I want a nucleophile with positive charge, no charge, or negative charge? Negative charge, that's the best for nucleophiles, right? And I see Annalise is saying cyanide, I like it. And alcohol would not be the strongest nucleophile. It's a weaker nucleophile in alcohol. Cyanide is a very good nucleophile because it's got a negative charge. The carbon, the atom with the negative charge is not too electronegative. It's carbon's not all that electronegative, so it can reach out that negative pair of electrons easily, polarizable. And it's not much steric hindrance behind it. This nitrogen is small, relatively small, so it's got little steric hindrance. That's a great nucleophile. And now what kind of solvent do I want? For SN2, it's the best solvents. I want polar aprotic. So what about, Let's go DMSO. I like DMSO. It's polar, it's aprotic. There we go. And my overall reaction, I'm going to keep this separate from the reaction, from the mechanism. Overall reaction will be CH3CN and sodium iodide. There we go. That's a great, very fast SN2. Now I'm going to do a very fast SN1. Oh, wait. I'm kind of rushing things here. I forgot. Let me do this. Let me do more with this SN2. So let's say overall first. The mechanism. I'll do it with color, why not? My goodness, come on, Jamboard. I'm gonna be so happy to be on a whiteboard after the semesters. Oh, there we go. Okay, here we go. So it's going to do a backside attack like that. Kick off our leaving group to give us iodide. And our nitrile. I want to make this linear, right? Because it's a that central carbon has just 2 atoms attached. There we go. And this is exothermic. So let's go all in on this. Let's do the reaction coordinate diagram too. Why not? Reaction coordinate energy. Exo. So I start here with my methyl iodide and my sodium cyanide. And here we go. Bimolecular rate determining step. Okay, so our transition state is going to look more like what? Reactants or products? Looks more like reactants. So my iodide is going to be just starting to break away. Still be pretty close to the carbon there. And my cyanide's bond is just starting to form. So it's going to be further away. And charge-wise, who's changing charge? The iodine starts off 0 and it goes to -1. So it's only just starting to get that negative charge. So I'm going to go like -1/4. And the cyanide starts off at -1 and becomes 0. So it's just starting to lose that negative charge. It's like -3/4. There we go. Oh, come on, man. Come on, zoom in for me. -3/4. There we go. Let me clean up this 4 over here. Bam. We got it. Makes sense? So now I want to consider SN1. So for SN1, we know the mechanism now. We have to make a carbocation first. That's the unimolecular rate determining step. So for SN1, what kind of electrophile do we want? And we know it has to become a carbocation. There was a question about this SN2. Did it have a solvent? Yeah, DMSO. Here's the solvent, polar rate product. And then now for SN1, is this electrophile that's going to have to become a carbocation? Do we want it to be a methyl electrophile, a primary electrophile, or secondary or tertiary? What would react fastest? Well, to make a carbocation, they're high in energy. 6. Let's look at this really quick. Grumpy carbocations. Remember our grumpy carbocations, the carbocation is short electrons. It wants more electrons. And if it has an sp3 carbon attached to it, those sp3 carbons donate and help out. I'll help out. Here you go. Here you go. Here you go. So the tertiary carbocation is lowest in energy because it has 3 sp3 carbon neighbors donating to it. Secondary carbocation is higher in energy. And the primary is methyl. They're so high in energy, we shouldn't be drawing them. They don't really form much in lab. But so yeah, so secondary and tertiary can do SN1 and E1, but methyl, primary and methyl can't. So we want to use a tertiary carbocation here. I mean a tertiary electrophile. So I'll draw this up, okay? And then my leaving group. I want a good leaving group. It needs to be very good, just like SN2, because it's in the rate determining step that it leaves. So what would be a good leaving group? Something comes off is very weak base. We can do bromide this time. Iodide is maybe a little better, but bromide is really good too. So we've got our tertiary electrophile. That's best for SN2. I mean for SN1. And now our nucleophile. What kind of nucleophile do we want? The nucleophile is not all that important as much. Do you know why the nucleophile is not as important if I want a fast SN1? Nucleophile is not as important because it's not in the rate determining step. The rate determining step is the unimolecular leaving of the leaving group to make a carbocation. Once the carbocation forms, the nucleophile, whether it's strong or weak, boom, it just flies in right away. So it's not as big a deal. Let's pick, we usually have like a weak nucleophile. Normally it's weak like water or an alcohol. So what would you like? Water and alcohol for this one. We'll go water, first thing that popped up on the chat. So we're going to make T-butanol in this case. Our bromide leaving group is off, and we make hydronium as well. And this is an example of solvolysis again, because the water is acting both as a solvent and a nucleophile and a base, actually. Okay, so we got our overall reaction here. And if you're not to the point where you're like, oh, I can see the overall product right away because I can see the mechanism in my head, then you, instead of just drawing out the overall products right away, you do the mechanism first and then add it into the overall. So let's do the mechanism. What's the very first step of this mechanism? Leaving group leaves on its own. Yep. The unimolecular rate determining step. Maybe this leaving group, maybe this molecule, this electrophile just gets hit with the side of the flask or another molecule of itself. And it makes the trigonal planar carbocation. Then the water, which is a weak nucleophile, can come in and add. Can come in from our side to be wedged or the other side to be dashed, but it doesn't matter for this molecule because it doesn't have stereochemistry. So the water is a weak nucleophile. It's not, water would not be good for SN2. You need a strong nucleophile for SN2 because it has to kick that leaving group out. But the carbocations are very strong electrophiles. They're very, very strong electrophiles because they're missing an octet and they have a plus charge. They're like vacuums. They suck in the nucleophile. They suck in that weak nucleophile, the water molecule. They're like, I used to say carbocations are like well, I said this about other things too. I used to say, oh, they're electron vacuums. They're sucking in electrons like a Hoover vacuum. But I don't think Hoover vacuums are so popular anymore. So maybe do we say a Dyson vacuum? Yeah, gotta say Dyson now. And not the cordless Dyson, the plug-in full power Dyson. Dyson animal ball. Yeah. Just drawing it in. So the way you think of it is this this water, which is a weak nucleophile, has to wait around for the carbocation to form. Then when it forms, boom, it gets drawn in fast. But let's also remember this first step was the rate determining step, the unimolecular rate determining step. This next step is much faster. And we get this water added on there, plus charge. And then another water molecule comes around and can deprotonate this. Boom, boom. Here, I'll make this colorful. I'll add green. To give us our final. Oops. Tap, tap, tap. There we go. Does that look good? Is my charge balance in each step? 0 overall charge, +1, -1. Okay, 0 still. Then this 0 charge plus charge. These two come together to make something +1. Yeah, balance. +1, 0, overall +1. 0, +1, overall +1. Looks good. So the water is acting both as a solvent. It's acting as a solvent to dissolve everything, you know. It's not actually dissolving this very well. This is non-polar and that's polar. These would be 2 layers actually. But they could react to the surface. So this reaction, I would have to like stir it or agitate it or heat it to boil it or something. But then this water, it's acting now as a nucleophile, then also as a base to deprotonate the thing. Okay, now this last step here, this is an acid-base reaction. This is the thing we spent a lot of time on. Is this product favored or reactant favored, would you think? Well, let's look at some stuff here. Let's look at the pKa's. So on the reactant side of this one, what's this? This is the acid, right? The reactant side acid. So it is got a pKa of about -2, right? Because it's like hydronium, -1.7. On the product side, what's our acid? The hydronium. If we reverse this, this would be the acid. So this is our product side acid, pKa of about -2 again, right? So wait a minute, K equilibrium is 10 to the -2 minus a -2, 10 to the 0, about 1. So we should have, it looks like about an equal amount of products and reactants, huh? So why am I having us draw this? I usually only have us draw reactions that are like very product favored, huh? This one's not so product favored. Want me to give you the reason why I like this one to draw it and to show it? Well, I think this does happen. I think almost all of our protonated initial product becomes deprotonated. And I'm going to have to ask the French for help. I know the French usually ask the USA for help, right? When I was in France, it was cool. They had a lot of their subway stations were named after our presidents, like Dwight D. Eisenhower stop, you know, and the other ones, because World War I and World War II, the US helped out France. But they did give us Louisiana Purchase. That was basically like a gimme. That was pretty nice. Anyway, so here we go. The way I'm going to figure this out is that I'm going to look at some concentrations. Usually for most reactions, you start out with maybe about 0.2 molar of your reactants. So it's maybe about 0.2 molar. And if waters are solvent, what's its concentration? About 55 molar. Yeah, so the water is way more present, right? So if I've got about 55 molar here, and let's say I've got about 0.2 molar here, then by Le Chatelier's principle, having a lot of water here will help force me to make more products, right? Large excess pushes equilibrium side by Chatlet's principle. Is this spelling right? Le Chatelier's. Does anybody know this? C-H-A-T. Thank you very much for the help. E-L-I-E-R. C-H-A-T. I-E-R. I-E-R. Le Chatelier's principle. Something like that, right? Okay, close enough. And even if you didn't know about Le Chatelier's principle, Chatelier, whatever. You can think about it. If there's so much more water, if a water molecules are definitely going to be hitting into this, right? And when they do, this one hydronium can get diluted in all the other waters and move away. And now this is less likely to run into another hydronium because there's just so much water surrounding it. So hopefully that makes sense to you. All right, let's also add into this information about exothermic endothermic, so we can draw out a reaction coordinate diagram. So tell me about this. This first step where the bromine just leaves on its own, when we break that bond, is that going to be exo or endo? The only breaking bonds, it's got to be endo. Takes energy to break bonds. This step has to be endo. And the next step, we're just forming a bond. Oxygen's forming a bond to the carbocation. So only forming bonds. What happens when we form bonds? Releases energy. It's got to be exo for sure. We don't have to be told that. We should just know that. But what about when we form the OH bond and we break an OH bond? Then we don't really know for sure if it's exo-endo, but I'll let you know. It's exo. And overall, I'm going to say this reaction's exo too. Okay, so we got enough information now. We know exo-endo, we know rate determining step. Let's do our reaction coordinate diagram. What I'll do is I'll snap this out, put this on panel 3 here. Make it a little smaller so I got room. So I start off with my bromide, my tertiary electrophile, endothermic step to make the first transition state. That's where the carbocation forms, and then a water molecule has to come in and react with that. And the next step's exo. I think it's gonna be. I think it's gonna be lower energy than the bromide originally. I wouldn't expect you to know that or worry about it. But then I add the H2O. Another water molecule comes along and deprotonates the final to get the final product here. Am I forgetting something? I am the bromide, huh? Okay, and then we got this and that, and there we go. Overall exo. Land. Here we go. And my transition states, a rate determining step. It's got the largest transition. It's got the largest activation energy right there, right? This one's pretty small activation energy. It should be. It's just forming that bond, huh? I'll make these all red. I like to understand it. It's getting kind of ugly. There we go. And then transition state 3 is here. That should be a pretty small activation energy. Acid base, Bronsted acid base reactions are fast. Okay, so let's draw them. Transition state 1, it looks more like the reactants. So, or no, more like the products. So that bromine is going to be just about fully gone. I'm going to emphasize it by showing it really far away. And then our charges. So the carbon is going to be almost a full carbocation. So it's going to be plus like 3/4. And the bromide is going to almost be fully negative. It's going to be negative 3/4. Got it. Transition state 2. Now this one's going to look like the reactants. So the water molecule is going to only just be starting to come in. Let me draw that nicer. So the charge on this carbocation is still going to be close to a full +1. So it's going to be about 3/4. And the water, what do you think? Is the water going to be, it's going between, the oxygen on the water is going from 0 charge to +1 charge. So where is it at in the transition state? Oh, shoot. Did I turn off the power? No. All right. And then the water is +1. The water's oxygen is +1/4. That's correct, because it's only just starting to get the positive charge. +1/4. There we go. All right, transition state 3. Hopefully they're getting easier for you all. We're doing a lot of them, right? This one's going to have a bond breaking and a bond forming, and it's going to look more like what? Reactants or products? Look more like reactants. So this is going to still be pretty short, and the new bond that's forming is going to be longer. And charges, so this oxygen, what's it going to be? +1/4, +3/4. +3/4. Oh. And the other oxygen? +1/4. There we go. We got it. Good work. Okay, so before I go on to E1 and E2, let me go to our chapter 7 PowerPoint slides. I'm going to go through my version. It's quicker. Document 12A, lecture PowerPoint, chapter 7. So SN1 reactions, we've gone over a lot of this already. This one's pretty good. It's got the stereochem involved. I'll do that one. That's a nice one. So that first SN1 was a simpler one because it only had no stereochemistry to it. This one here now will have some stereochem. So let's try it. Oh, let me just type that up. That seems better. So let's check this one out. So to start, what sort of electrophile do we have here? Is this a methyl electrophile, a primary, secondary, or tertiary? This is the tertiary electrophile, and that's great for SN1 because it can form the carbocation pretty quickly. So this tetrahedral carbon now is trigonal planar as that leaving group bromide leaves in this rate determining step. Unimolecular rate determining step. Okay, so this is key here. This carbon right here with leaving group, it went from tetrahedral geometry because it had 4 things attached to it, and now it's trigonal planar. And it's a tertiary carbocation again. It has this sp3 neighbor. I'll help. sp3. I'll help. This one's not actually as helpful because it's sp2, but it's still going to be good enough to react. All right, now our methanol. What do you think about that methanol? Is it a weak or a strong nucleophile? So is the methanol a weak or a strong nucleophile? So strong nucleophiles, what charge do they want? Strong nucleophiles want negative charge. This is a weak nucleophile. It's a weak nucleophile. It has to wait around for a carbocation to form. This is a tertiary electrophile, so it couldn't do SN2 just from crowding. But if this weren't a tertiary electrophile, like if I had another electrophile, like a primary one, like this iodide or something, this will not do SN2. It's too weak. Not a good nucleophile. I mean, it is a nucleophile, but it's weak. And so can't do SN2 with that. It has to just wait for a carbocation to form because it's weak. And once the carbocation forms, though, then it just gets sucked in. It's like gets drawn in. It can't help itself. It doesn't matter that it's weak because the carbocation's an electron vacuum. And if it gets drawn in from this side, then it makes the following. And this goes back to tetrahedral. And when it comes in from the bottom, it makes the, let's see, A, B, C. This is the S stereochemistry. And then my carbocation, if I want to redraw it, I'll redraw it so we don't get it mixed up here. Trigonal planar carbocation here. The weak nucleophile methanol can react with the electrophile also from the top, wherever it hits, basically. I don't like the look of that. I'll put my carbocation on the other side, it's easier to see. And if it attacks from the top, it gives us the enantiomer. And if I calculate the RNS, it is definitely the enantiomer is A, B, C. Yeah, this is R. Okay, so what do you think? Does it look like one of those is does it look like one of these products is made more than the other? Or do they look like they're produced the same? Actually, you'll make the same amount of both. It'll be a 50-50. You'll get 50% this and 50% this. You might be thinking, oh, I've got an oxygen on this side and a methyl on this side. They're different, oxygen here, methyl here. But the reality is this is a single bond and it just rotates around. So the methyl and the oxygen are spinning around like a fan blade. So either side is the same. You're only going to get a difference in size if you have a stereo center outside of if this was a stereo center outside of the carbocation, then you definitely have a difference in the size. So you get a 50-50 mixture. And then the final step is just the water molecule, another methanol coming in and deprotonating. That did not look pretty. Oh, I'll do it in black. I'll do it black. Yeah, just keep black. Here we go. There we go. There we go. So we get 50% that. So we're getting a racemic mixture here. I'll say for this one, you later when you're going over your notes, do-yo this one. Do on your own. Do-yo to give the other 50%. Okay. This last step too, is this product favored or reactant favored or what's going on here? Let's check it out. So the reactant side acid has a pKa of about -2. Product side acid has a pKa of about -2. But the methanol is the solvent in high concentration. So by Le Chatelier's principle, it'll push it to the product side. I think methanol's maybe like 30 molar or something. You can just look up methanol's density and molar mass and calculate it. Okay. So we get a racemic product. So this was an interesting example. Our reactant initially was chiral, but we got a achiral product mixture. So when you start chiral, it doesn't always mean you're going to get a chiral product mixture. Because we lost chirality when we made that carbocation. And then if you consider, I'll explain why it's achiral. Hopefully you already know, but so if I zoom in on this. So this is going to be made 50%. This is going to be made 50% of this is going to be made. And this, if this is like -7 degrees rotation, this would be +7 degrees rotation. So they'll cancel out. Ryan, you're asking about if the carbonyl was wedged or dashed. I'm not sure what you mean. I'll tell you what I'll do. I'll give you an example where we will go from chiral to chiral. I'll show you real quick. Let's look at this. Easiest one will probably be one with a ring. Let's go. I'll put like a wedge here, and then I'll put like a dashed iodide. So can this one undergo SN1? I've got what kind of electrophile here? I got a secondary electrophile. Can it do SN1? When I say that, I mean, can it form a secondary carbocation? Yep, can. And then what kind of nucleophile do I want? Should I have like a really strong nucleophile like cyanide or hydrogen sulfide? I shouldn't actually. I don't want a really strong nucleophile like that because this secondary electrophile, it can undergo SN2. If I added cyanide, it'll just do SN2. It won't do SN1. So I don't want a really strong nucleophile here. I can use water again. Water's a nice, easy one. H2O. Oh, and I'll talk about this shortly. I'm going to keep this reaction cool. That's going to favor SN1 over E1. We'll get to that shortly. And what I'm going to wind up with is two products. An iodide leaving group. And how are these two related? They're the same molecular formula, same connectivity. Are they mirror images? Nope. They're diastereomers. They're not mirror images. As far as R and S goes, they're A, B, C. This one's R. This one's R. And A, B, C. This one's R. And this one's S. Yeah. They're diastereomers. So if I have like a +11 degree rotation for this, this one might be +21. They're not going to be opposite or anything. And besides not having the same rotations, they will not be producing the same amount. There's going to be more of which one, do you think? More of the trans. It might be like 80% of this and 20% of that. Now that when you make the carbocation, there's going to be less steric hindrance from one side. I'll show you. I'll do the mechanism real quick. Hopefully you've gotten to the point now where this mechanism is just kind of in your head. Oh, and then before I do the mechanism. So I started off with a chiral reactant. And I ended up with chiral product mixture. Okay, so mechanistically, we'll find out why this happens. It's easy enough for us to do. We're getting good at these, hopefully. First step of the mechanism, leaving group leaves. Man, let me draw in my hydrogen here so we can see that this makes sense. I've still got this hydrogen, but now it's trigonal planar, right? And then my water is a weak nucleophile. It had to wait around. If water were a strong nucleophile, it would just do SN2 right now. We wouldn't get the multiple products. We'd just get the inverted product only. But water's a weak nucleophile. It couldn't kick off that iodide. It had to wait patiently for the carbocation to form. And then once the carbocation forms, it can attack because the carbocation is such a strong nucleophile. Let me not forget to add my iodide that left. All right, and then when water adds, it can add from either side. Oops. It can add to that side or to the other side. Oh my goodness. Colors, colors, colors. Here we go. There we go. So which side is it easier for the water to attach to? The backside, less steric hindrance. So I can see getting maybe like 80% of this and like 20% of that because there's steric hindrance from the methyl. And then the rest of the mechanism, you can do that just to protonate with the water. Do on your own, do on your own. Got it? So you can see sometimes you have a chiral reactant and it makes a chiral product mixture. Other times you can have a chiral reactant that gives you a chiral product mixtures. And then, so it's not like a, oh, just memorize a pattern. It's not that, it's draw out the mechanism. Think about it, look at steric hindrance, figure it out. Just derive it each time. So SN1 factors, things to consider. So the electrophile, we need that to be what for SN1? Could we do an SN1 with all the electrophiles, methyl, primary, secondary, tertiary, or just some of them? Only some of them, yep. And then I got a question about homework 6 due date. Check today's lecture outline or yesterday's or the, yeah, check that stuff. All right, so here we go. Electrophile is, it's got to be secondary or tertiary only. The methyl and primary, these ones, their carbocations are too high in energy. Can't form the carbocations. Oh, the leaving group now, it has to be a good one. Has to be good because it's in the rate determining step. It pops off, has to come off by itself in the rate determining step. In the unimolecular rate determining step, right? And the nucleophile, usually weak. Because it's not in the rate determining step, it doesn't really matter. Once the carbocation forms, then it's like, then the nucleophile gets drawn in. Okay, now solvent, we haven't talked about this yet. The solvent, polar, protic is best. So it's different than SN2. Because the polar protic solvent, because the formation of the carbocation, it creates a lot of charge. You got like a positive charge, leaving group used as a negative charge to it, partial charges to it. And then a polar protic solvent's able to stabilize those negative charges. And we don't have to worry about the polar protic solvent slowing down the nucleophile like SN2. So I'll type this up. The rate determining step has lots of charge, partial charge. A polar protic solvent rate determining steps transition and if it stabilizes that charge of the transition state, that means that that transition state is lower in energy, activation energy is lower, faster reaction. And we do not have to worry about the nucleophile being overly solvated by solvent, because it is not involved with rate determining step like SN2. For SN2, the polar protic's not as good as polar aprotic, but SN1 it's better to have polar protic. All right, so let me see. Let me get back to where we were. So we got that. We got, yeah, these are good ones. So let's rank these in terms of how fast they'll react in an SN1 reaction. Which of these electrophiles will react the fastest in an SN1 reaction? These are iodides here. I'll put the lone pairs on them so they stand out a little more. So which of these electrophiles is best for SN1? Tertiary, fastest for SN1. Yep. Who's second fastest? Secondary. Tertiary is fastest because it makes the most stable carbocation. It's an endothermic step. The rate determining step looks like that carbocation mostly. So it's going to be lower in energy. A transition state that looks more like a tertiary carbocation will be lower in energy than a transition state that looks more like a secondary carbocation. And then this primary carbocation, we'll just say no reaction. It's so slow that it doesn't even react, because to form the primary carbocation, it's like way up in the catosphere. It's too high in energy really to happen. And then the methyl, it's even higher in energy. So no reaction again for SN2. What about though I'm sorry, that was SN1. What about for SN2? Let's switch this up. So let's rank these not according to SN1, but now according to SN2. Which one reacts fastest in an SN2 reaction? So methyl will be fastest. Methyl's fastest, least steric hindrance, huh? Biggest cone of reactivity. Primary is second fastest. Secondary is third fastest, and the tertiary, no reaction. No reaction. When I say reaction, I mean no SN2. It can do SN1, but no SN2. Too much steric hindrance, huh? Okay. We're getting there. And then this is showing, this slide's pretty interesting. It shows carbocations, and it has these computer generated images of them predicting like the charge. So here's a methyl carbocation. This is the very high energy carbocation that's so high in energy, we aren't going to really make it in our labs, normal situations. And it's got an empty p orbital here, trigonal planar. And then it's got a lot of blue. Blue's representing positive charge. And then when we go to a primary carbocation with a methyl there, it's donating some electron density to the carbocation. So it's a little blue. The blue area is smaller, right? So primary carbocations are lower in energy than methyl, but they're still just too high in energy for us in lab normal situation. Then we got a secondary, 2 sp3 carbons donating. Now this we can make, and we can use secondary carbocations. And then the tertiary, 3 methyls donating. And how do they donate? People hypothesize it's like this kind of like half a pi bond. It's called hyperconjugation. This is our sp3 carbon donating through hyperconjugation. I just say memorize that sp3 carbons are electron donating. Got it. All right. That's a pretty good one. Do I want to do it? Yeah, I'll do this one. Rainbow bubbles, I like it. All right, so we're going to rank these electrophiles according to their reactivity in an SN1 reaction. So what we're looking at here is, we're asking here is, what is the best leaving group? So how do we tell if something's a good leaving group? Well, we have it leave. So I'm going to show all the leaving groups leaving and decide which one's the best. There, I'll make this red too. How to make it stand out? There we go. Okay, here we go. This is our initial rate determining step, unimolecular. Makes the trigonal planar carbocation, and this one makes water as our leaving group. Oh, no, it does not make water. This one's going to make hydroxide. And this one's making the same carbocation, but water as our leaving group, huh? And this one we're going to make ammonia. Okay, so what we're doing basically here is just ranking these leaving groups. These are the leaving groups. So which of these 3 do you think is the strongest base? What's your guess? Hydroxide, water, or ammonia? Hydroxide is like sodium hydroxide, you know, in lab, it's a strong base, right? Okay, and then which is the weakest base? water. So the ammonia is right in the middle there. How do I know these things? One way you can know them is by knowing some pKs, which you know. The conjugate acid of hydroxide is water, which has a pKa of about 16, right? The conjugate acid of water is hydronium, which has a pKa of about -2. And the conjugate acid of ammonia is ammonium with a pKa of about 9. So if you look at these, you'd say, oh, the hydronium's the strongest acid here, so its conjugate base must be the weakest. And water is the weakest acid, it must have the strongest conjugate base. Okay, so finally then, rank the electrophiles, rank the leaving groups, I'm sorry. Leaving groups. And we said earlier with SN2, and it applies to SN1, when you take the leaving group off, the weaker it is as a base, the more stable it is as a base, the better the leaving group. They correspond. So our best leaving group is our water here. Fastest leaving group. Like it comes off the easiest. So this is like number 1. And then our worst leaving group would be hydroxide, slowest to react. That'd be 3. This would be like 2. So what I'm getting at is this is the fastest reaction. And this is the slowest reaction. I'd say this is so slow that it's borders on no reaction. I would say it's just like no reaction because that's such a bad leaving group. Ryan, you were asking about the size of oxygen and nitrogen. They're right next to each other on the periodic table on the same row, so their size is about the same. It's more about their electronegativity. When you're on the same row of the periodic table, the oxygen's more electronegative. But if you're comparing oxygen and nitrogen, you want to compare like, or if you're, I'm not sure, were you comparing water, oxygen, and nitrogen of ammonia? That makes sense to compare those because they're both no charge. Okay, good. All right. So yeah. Got it. Let's see. Hopefully this is good stuff here. We went over the solvents and the nucleophiles. Yeah, I don't love that one. Okay. Oh wait, I didn't do E1 yet. Oh, I just don't have a lot of details on E1 in this thing. Okay. So let's talk about E1 for a little while because E1 and SN1 are very similar. They have the same first step. Okay, E1 elimination and E equals elimination and 1 equals unimolecular rate determining step, and it's exact same step as in SN1. So it's kind of easy to learn about E1 after you've done SN1 because you've already got like kind of almost half the mechanism. Okay, so let's look at an example. Let's go. I'll just do a really simple one first. No, I'll make it a little bit more complicated. Let's go this way. Let's go. I'll wedge this out. I gotta iodine. I'll do that. I'll do this one with ethanol. And I'm going to add heat. Heat favors E1. I'll explain why shortly. And what we're going to get here is a number of products. Actually, before I draw them all out, I'll do the mechanism first. All right, there we go. Mechanism first. All right, what kind of electrophile do I have here? Secondary electrophile, good. So can a secondary electrophile form a carbocation? Yes, it can. And that's the first step of this mechanism. There we go. And now this is key. Students confuse this at first, but in the past, but not you guys. Not you all. You all are going to get this one. I want to make sure you really understand what's going on here. This is our carbon with the leaving group, right? In an E1, you have your carbon with your leaving group, and then you can't get it mixed up. You got to know that you're going to next, after you make the carbocation at the carbon with the leaving group, you're going to deprotonate one carbon away. So this carbon right here is one carbon away from the carbon with the leaving group. It's attached to the carbon with the leaving group. And we also have another one carbon away over here that we can deprotonate. Okay, so let me show you that. So I'll do this side first. So I'm going to put a hinge right here. I'll throw on a green bond. So this stands out. And then the ethanol that comes by. This ethanol, it's going to act as a base in this elimination reaction. Is the ethanol a strong base or a weak base? What's your guess? Weak base. Not very strong. So it can't go and deprotonate the electrophile before it loses the leaving group. It has to wait around. It's like weak base, like, what's going on? Kind of kicking the pebbles. Like it's at the dance and it wants to get involved in this reaction, but it's too shy. It's up against the wall, just kind of, oh, wow. Well, I wish I could dance with them. They're so pretty and they're so confident. Has to just wait. But then when the carbocation forms, and the leaving group leaves, then whoa, they get drawn in there. It gets them over their shyness. And they get pulled in and boom, they deprotonate one carbon away. And then swinging on a hinge, this green bond will come down to make a bond with the carbocation, because this carbocation is missing a bond right now. It only has 3 bonds. So that hydrogen there. Oh, this first step was a rate determining too, huh? Rate determining step. Okay. Oh, and I didn't draw the, oh, I did. Never mind. All right. So now my first product is the following. I got an alkene. E1 and E2 reactions make alkenes. And that's it. Get protonated solvent here. And we're done. I make that alkene. This is referred to as a monosubstituted alkene. Monosubstituted means it's an alkene, a carbon-carbon double bond that has 3 hydrogens and 1 alkane chain, 1 alkyl group, replacing what, if you just had ethene, just CH2, CH2, they have no alkane chains on it. This has 1 alkyl chain. It's a monosubstituted alkene. That's one product you can make. The other products you can make, I'll show that mechanism by I'll show this one. I'll redraw the carbocation. So the next products, and I want you to redraw these carbocations. I don't want you to draw like a bunch of curved arrows to the same carbocation. It makes you make mistakes. So I'm redrawing the carbocation. All right, and now I can go 1 carbon away, and I have a hydrogen here. Boom, and I can draw a little hinge right there. This does have another hydrogen here too, but it's only, I'm going to show it reacting with that one. And again, it'll be our weak base ethanol that had to wait around for the carbocation to form. And it comes over, it deprotonates 1 carbon away. That pi bond, that sigma bond swings over to become a pi bond. And we've got our product. And we'll get actually 2 products in this one. You get this product plus this product. You're probably asking, wait, how did that happen? I'll explain how. So first, let's talk about these two. These two are actually, both are di-substituted alkenes. They're di-substituted, and what that means is they have 2 alkyl groups attached to the carbon-carbon double bond to the alkene. So you got 1, 2, 1, 2. They are different in that this one is called trans disubstituted and this one's cis. How are they related, these 2 molecules? So they both have the same molecular formula. They both have the same connectivity. They have an alkene between carbon 2 and 3. Are they mirror images? No, these are diastereomers. All right, but how did this, it looks like this one should be the only one formed by looking at my carbocation, right? Anybody confused with that? So like this cis one, is anybody thinking, what? How? Right? What? How? Well, the thing is, you have to consider that the original molecule, before the original electrophile, it's not stuck in this zigzag form. We've done Newmans of things like this, right? So this guy can switch around to be like this, right? It switches around so that you can see maybe, oh, wait, I can see if this forms the carbocation, then it can lead to that one, right? Also, the carbocation can, once you have the carbocation from either one, it can rotate around before it becomes the alkene, right? So that's why you get both of those. Okay, so as I said, I was gonna draw the mechanism and then come back and fill in my overall product. So my overall products are gonna be, I'll get the monosubstituted alkene, disub-cis, disub-trans, the protonated ethanol, and the iodide. Got my overalls all filled in there. And I think that's a good pausing point. Next time, maybe I'll do the, remind me, I'll do the, what is it called? The reaction coordinate diagram for this one.